So, in this lecture we shall be talking about design representation. Now, earlier I had said that you can create a design using a hardware description language, Verilog, with respect to this course. Suppose we create a design in some hardware description language like Verilog. Now, the question arises, at what level do we typically create the design, or how do we create, how do you visualize a design? So, when we talk about design representation, what we mean is that given a design, how we can visualize the same design from different angles. Now, the way we shall be presenting here is that there are three distinct ways or three distinct angles from where you can visualize the same design, and the implications will be a little different. Let us see. So, design representation, as I said, this talks about how we represent a design. A design is nothing but you can think it as a black box that is trying to perform its intended operation. You have designed that block to carry out certain operation, and that is your design. Okay. Now, design representation we are considering at three different levels. One, you are calling it as behavioral, structural and physical. Now, with respect to Verilog coding, these terms behavioral and structural will be coming repeatedly, and we will be understanding the exact differences and how we can code behavioral and structural designs in Verilog in a very efficient way. And of course, the third representation is physical. Now, there is a very interesting way to just express this design views or viewpoints. It is with respect to something called a Y diagram. Now, this name has come because it has a shape of a Y. So, you think of an imaginary Y with the three design representations in the three directions. Let us say this is our behavioral domain, this is our structural domain, and this is our physical domain. Now, just along each of these domains, like for example, means in the axis of behavioral domain, here we are talking about a design in terms of its behavior. Like in a very high level case, you can think of an algorithm or a program, you can think of a specification, you can think of Boolean expressions, you can think of truth tables, state diagram and so on. These are all examples of behavior. Now, when we talk about structural domain, now well means we had explained in the last lecture what is a netlist. A netlist is nothing but some blocks, building blocks and their interconnections. Now, these building blocks can be defined at various different levels. Depending on that, our structural domain specifications can vary. So, it can be at the register transfer level, it can be at the functional level, it can be at the gate level, transistor level and so on. And talking about the physical domain, here you are actually talking about the implementation. Like in the ultimate case, when the final design is complete, we would be getting our chips or a printed circuit board. Before that, well, our designs will be placed on a silicon layout in terms of cells. Now, what will those cells contain? They will contain some transistors which will have some layout. So, these are all implementation or physical design related things, that our chip, the cells that are put on a chip and the transistors that make a cell. So, here we are looking from an angle which talks about the actual implementation. Okay. So, in one side was the behavior, one side was the netlist view and the other side was the actual physical implementation view, right. So, these are the three viewpoints. Now, there are some interesting ways to look at these Y. Let us look at it once more from this point of view. Here we have showed it in a slightly different way, behavior, structural, geometry, and you see we have drawn some concentric circles. The outermost circle indicates the most abstract design. So, at the behavioral level, this outside circle indicates systems. It's like in the highest level, my system may consist of 2 processors, 1 memory and 1 I/O module. This is my highest level design of the system. Okay. So, this is my behavior. So, this in the structural level will be a netlist that consisting of interconnection of CPUs and memories, as I have said the example. And in the physical level, this will consist of some chips, a collection of chips, one may be a processor, one may be memory and so on. Okay. So, as you go to the inner circles, you are carrying out synthesis, you are refining your design. Like at the next level, your behavior is your algorithms. Here you have subsystems and buses, here you have some clusters. Next level you have register transfer level blocks, you have ALUs and registers netlist level, and here you have macros and floor plans. Next level inside you have logic cells, gates and flip flops. So, here you have connection of gates and flip flops, here you have cells, module plans, and at the lowest level you have the transfer functions, transistors and polygons. So, as you go from the outermost circle towards the innermost circle, from all the 3 viewpoints your design is getting refined from very high level or abstract. See, from a very abstract level, in the behavior you will say that, well, I want a computer system. In the structure level you will say that, well, I need 2 processors and 1 memory block. Now, in the physical level you will say that, well, on the board I need 4 chips. These are the different ways to look at the same thing. So, as we move towards the center of the circle, each of these blocks will get further refined, they will get more detailed out, and we will be having some kind of a top down design process. Now, if you think of it, well, we normally do not do it this way, that at one level we have all the 3 viewpoints, then we go to the next level, again look at all the 3 viewpoints. So, we really do not work exactly in that way. Rather, we work in an alternate way, which is shown in the diagram on the right. So, here I am showing the behavior axis here, structural here and geometric here, or the physical here. Now, you see, actually here I am giving an example. We start with an algorithm at the behavior level. So, highest level is algorithm. So, we carry out some transformations in a systematic way, which is represented, you see, as a helix here. From the outside you slowly move towards the innermost point of this structure. So, from the algorithm you translate into processor, which you translate into a chip floor plan, and each of the blocks in a chip floor plan you translate into finite state machines. They will be translated into registers and ALUs, they will be translated at the physical level into modules, which will be placed, module placement. Then each of these modules will be having a description at the behavior level, module description. Now, each of the modules will be designed as a netlist, we call them as leaf cell, they will be placed, cell placement. Now, each of the cell will be expressed as Boolean expressions, they will be realized using transistors, and finally, they will be realized using the layout masks. So, you see, this helical structure is more natural in terms of the steps that a designer actually follows. So, although that concentric circle is a good way of representing, but the actual process that we follow is this helix. From the outermost point, we slowly move towards the center of the Y. Okay. This is the so called top down design process. Okay. So, let us again come back to the behavior representation. Here we shall be showing you some examples in Verilog. So, just to repeat, in the behavioral representation we specify how a particular design should work. That means, given a set of inputs, what should be its output. So, here we are not telling that exactly how the design has to be implemented. Some examples of behavioral representation are Boolean expressions, truth tables, table of input and output values. So, you can write algorithms in some standard high level language like C, that is also a behavior, or algorithms written in hardware description languages like Verilog or VHDL. These are all examples of behavioral representation. Now, let us take an example, a simple example of a full adder. So, a full adder will have two inputs A and B and a carry input C. So, it will be generating a carry output and a sum like this. A, B, C are the inputs and S and C y are the outputs. Well, now I am not trying to explain how a full adder works, you already know the basic definition of a full adder. I am just writing the logic expressions of the sum and carry. So, the sum and carry expression in terms of A, B, C will be this: A B bar C bar, or A bar B bar C, or A bar B C bar, or A B C, which is nothing but A exclusive OR B exclusive OR C. So, it is the exclusive OR of the 3 inputs, that is sum, and carry is nothing but A B or A C or B C. So, this is one way of expressing the behavior of a full adder, because here you are not specifying what kind of gates to use, how many gates to be used and so on. We are just writing down the expressions and we are telling that, well, this is your sum and this is your carry, this will be the behavior, right. This is an example. Now, this is in terms of Boolean expression. The same thing you can express in Verilog as follows. Well, I have not talked about the syntax of Verilog. So, possibly this is your first look at a Verilog program. Let us see what it contains. The syntax is somewhat similar to the language C. Here every statement ends with a semicolon. This is like a function in C. This is called a module. So, a Verilog program will consist of one or more modules. So, it starts with this keyword module, it ends with end module. This module is followed by the name of the module and the parameters. The parameters are, well, in terms of the hardware, these are nothing but the input and the output ports of that block. Now, for a full adder, the inputs are A, B, C and the outputs are carry out and sum, right. So, this S, C, Y, A, B, C are the 5 parameters. We declare A, B, C as input like this: input A, B, C, output S, C, Y. So, that the CAD tool will know that which are your input pins, input signals, which are your output signals. And there is a assign statement available in Verilog. Here we are showing it. Using assign, you can directly write down the Boolean expression. This hat is the expression for exclusive OR. This indicates XOR. So, sum is A XOR B XOR C, and this ampersand is AND, bar is OR, carry is A B or B C or C A. So, you see in Verilog you can express a Boolean expression which is a behavioral specification very concisely in this way using the assign statement. Okay. So, this is one way to specify a behavioral specification in Verilog. Now, this same design, the full adder, I am showing only one of the output, the carry. Well, just if you recall, the carry is nothing but A B or B C or C A. So, you tell me when the carry will be 1. The carry will be 1 for several conditions of A, B and C. When either A and B is 0, but C is A, B is 1, C is 0, A and C is 1, B is 0, or B and C is 1, A is 0, or all these 3 are 1. So, for these 4 cases my carry will be 1. For all other cases carry is 0. For all other cases carry will be 0, right. So, this I can express also as a truth table. So, how do I express? Well, I need not have to specify all the rows. I can simply say that at least 2 must be 1, A B, A C or B C, at least 2. If it is 1, then the carry will be 1. This is what we are specifying here, you see, in this truth table. So, this is again a way to express a behavioral specification in Verilog in terms of the truth table. So, there is a keyword called primitive. So, we use this primitive keyword here. So, I am only showing for carry. So, there are 4 parameters, this is the output, A, B, C are the inputs. So, I declare the input and output signals. So, I use a keyword table. So, here this is a comment just for showing that these are the values of A, B, C and this is C, Y. This is a comment line just for convenience. And the way you specify the input is you specify 0 or 1 and question mark means do not care, and colon separates inputs and outputs. The first line says if A and B they are 1, but C is do not care, then carry is 1. Like you see here, I mean if A and B are 1, C is 0, then also carry will be 1, but if A and B are 1, C is 1, then also carry is 1. So, actually C is a do not care, it does not depend on C. So, this we can write in a concise way using the do not care notation. Similarly, if A and C are 1, B is do not care, or B and C are 1, A is do not care, then also carry will be 1. But on the other cases at least 2 of the inputs are 0, A B 0 or A C 0 or B C 0, other is do not care, then carry will be 0. So, you see if we use do not care, then instead of the 8 rows of the truth table, here we require only 6. So, our specification may be shorter, right. Okay. Now, let us move on to structural specification. Now, in a structural specification, as I said that it actually specifies how some modules are interconnected. So, when we say that I am defining something in a structural way, which means I will have to specify the modules and I will also have to tell how they are actually interconnected. Okay. Let us see an example on this. So, earlier we mentioned that this kind of structural representation is also called a netlist, and netlist can be specified at various levels, at a very high functional level, gate level, transistor level and so on. This we will see later slowly. So, structure level, levels of abstraction, this also we talked about earlier, I mentioned gate level, transistor level, or it can be a this can be a hybrid design also. Some of the blocks can be in the gate level, some of the blocks can be at a higher level. Okay. So, as you move down, more and more details are revealed. Like a netlist which is at a functional level, multiplexers, decoders, adders, their number of blocks will be less. So, as we move down to the gate level netlist, equivalent netlist, number of gates will be much larger. As we move down again to a transistor level netlist, number of transistors will be even larger. So, as you move down, your size of the netlist will be increasing gradually. Okay? Fine. Let us take an example to illustrate structural design. Now, this is a circuit which you must be familiar with. This is a 4-bit ripple carry adder. So, what we have done, just to recall. So, a 4-bit ripple carry adder consists of 4 full adders. So, I want to add 2 numbers A0, A1, A2, A3 and B0, B1, B2, B3, they are all 4 bit numbers. So, I feed the corresponding bits to the 4 full adders, and C0 is my carry in. The carry out from the first full adder will be going as carry in to the next, carry out from here will go to the carry in of the next, similarly here, and C4 will be the final carry out, and S0, S1, S2, S3 will be the final sum. So, if you look inside the full adders, we had just now some time back we saw the behavioral specification of a full adder. We saw that there is a sum part, there is a carry part. There will be one circuit which will be computing the sum, there can be another circuit disjoint or shared maybe which will compute the carry. Okay. So, each full adder will consist of a sum circuit and a carry circuit. So, conceptually speaking, we show it like this. So, as if we have a 4 bit adder, we call it as add4, 4 bit adder. 4 bit adder consists of 4 full adders, add, these are full adders. Each full adder consists of a carry circuit and a sum circuit, carry circuit, sum circuit. So, this is how we can describe a circuit in a hierarchical way and also structural way. Like every adder will be a combination of carry and sum, and this 4 bit adder will be a combination of 4 full adders. Now, this carry and sum you already know, these are the expressions. Okay. So, let us see in Verilog how we can do this. So, here I am showing the top level module of a 4 bit carry lookup adder. So, here the parameters are specified here. Well, here I am not going into the detail because all these details we shall be explaining again later. I am just showing you how this Verilog code looks like. Just one thing you see here, here I have declared x and y are the inputs, and this x and y input I have declared as a vector. 3:0 means it is a 4 bit number, where the bits are numbered from the most significant side 3, 2, 1, 0. This is the way to specify in Verilog 3:0. Carry in is a single carry in. Similarly, output sum is also 4 bit 3 to 0. See, we here let us show here. I mean, say we have an adder. We have also defined a full adder. Add is a full adder. Full adder has parameters carry out, sum, and the 3 inputs. So, you see here in the 4 bit ripple carry adder, I have made 4 copies of this full adder. This is called instantiation. Well, in a C program, when I call a function, so the control goes to the function gets executed, and again we come back. But in terms of hardware, if I call a full adder 4 times, it means I am using 4 copies of the full adder. This is called instantiation. So, here 4 copies of the full adder will be instantiated, and I am giving different names B0, B1, B2, B3 to the 4 copies. And this parameters, the way I have given the name, this defines the interconnection. Like here, for example, for B1, the carry out C out 0, this will be C out 0. So, this will be connected to this. C out 2, C out 1 will means for B0, the carry out will be connected to the carry in of the next. For B1, the carry out will be connected to the carry in of the next. For B2, the carry out will be connected to the carry in of the next, and so on, because this is your carry in, the last parameter, right. And here this is a hierarchical design. The full adder also we have defined in a structural way. We have put a sum and a carry. Sum is a module, carry is a module, we have instantiated them, and sum and carry similarly can be described like this. So, I have defined this in a structural way, not in a behavioral way. You see, sum, this A, B, C in are the inputs, sum is the output, and T is a temporary wire. This XOR is a gate. What does this TAB means? TAB means the first one is the output, second two are the inputs, which means that I have an XOR gate where the output is T and the inputs are A and B. The first line indicates this. Then next line indicates there is another XOR sum is the output, the inputs are T and CY in. So, T is there is another XOR gate, there is another input CY in and you generate sum. So, you actually specify this circuit. This is structural because you have specified two gates, XOR gates, and how they are interconnected, right. So, this is a structural description of a sum. Now, these gates XOR or for carry this AND OR, these gates are already there as part of the Verilog language. So, this we shall be studying slowly. So, I have just shown you an example here just to show you how a Verilog module looks like. So, in the carry block in a similar way, we need 4 gates G1, G2, G3. This will do a AND of AB, AND of AC and AND of BC, and the outputs are T1, T2, T3, and finally, you do a OR of T1, T2, T3 and out. You see the number of inputs to the gates you can vary, like in the last case the first one will be the output and the remaining 3 will be the inputs. So, this will be automatically taken like this, right. Fine. Now, talking about the physical representation, which is the lowest level, here as I said that when you finally fabricate the chips, you define a large number of various polygonal shapes for the different layers of fabrication. Okay. So, these are the specification of so called photo masks that are required in the fabrication process. Now, this 4-bit adder is the way we look at it from the function of the structural point of view, but from the physical point of view there will be a large number of rectangles or polygons. So, this also can be specified in Verilog. I am just showing you an example, this is not the complete description, just a partial description for the adder. Like you can actually define some coordinates, 0, 35 is a coordinate, this aluminum means this is an aluminum wire of width 1 unit, this is a polysilicon wire of width 2 units and so on. So, in this way you can define various wires of different metals or materials, you can specify the widths, basically they are rectangular shapes, right. Rectangles, there will be a large number of such rectangles you will define in your specification. So, I am just showing you these primitives are also available in Verilog. So, when you go down to the layout level, the same Verilog language can be used to specify your layout. Okay. This is what I meant by saying is that you have a hardware description language, and as the process of synthesis continues, you transform one version of Verilog to another version of Verilog, that another version of Verilog to another refined version of Verilog. In that way you proceed, and at the final step you get a description which is your final layout description. Okay. Fine. So, just a quick look at the digital IC design flow once more. Starting from the specification, you design entry, or this may be your specification in your Verilog or VHDL, logic synthesis, and there are some steps where you are actually going for the physical design. This is called physical design. You go for partitioning, floor planning, placement, routing, steps like this. And in the first steps, you go for design entry, logic synthesis, partitioning. These steps are typically called front end design or logical design, and these are called physical design or back end design. And there is some feedback connection also, because at some step you may find that it is not working properly, you do simulation, you may have to go back and make some changes. Like here also you can do some circuit extraction and simulation, you see that your delay is not coming proper, you may have to go back and make some changes. Okay. So, just a very rough view of the whole process of design, front end design and back end design. This entire process have to be traversed by a designer to actually design a circuit in terms of the final layout description starting from the behavior. Okay. So, with this we come to the end of this second lecture. Well, in this lecture we have basically talked about design representations, the three ways you can visualize a design, and we have seen some examples in Verilog, how Verilog can be used to capture the design at the different levels of abstraction, different views, behavioral, structural and physical. Thank you.